Feed and Gas wiki page. So welcome everyone to this webinar within the Global Methane Genetics Initiative. I think it was prepared by the project partners within the Danish and the Dutch Holstein project, where one of the one important activity is to set up guidelines or how to record methane with sniffers and provide guidelines and harmonization standardization across countries. So I think it was Coralia from the Wageningen group and Trine from Denmark who were in charge organizing this mainly. So thanks a lot for this. We have 53 people joining today, so it's I think that's a good sign that is really a very important topic. How to get a methane phenotype and data editing quality in place from sniffer data. We are very happy. So today, 4 presenters will give a presentation and present their developed pipelines. So we will start with Coralia Manzanilla-Petsch from Wageningen University and Research, showing the Dutch pipeline, and then followed by Oscar González Recio, who has also developed a pipeline. And then we have Lucas Alcantara from Canada. And then in the end, we have Victor Milkevich. I hope that's the right pronunciation, Victor, who has already very long experience analyzing our sniffer data. So a little bit of housekeeping before we get started. So we will do the presentations in a row. So each of the speakers has 15 minutes. If you have any questions, so please place them just in the chat. After the presentations, we will then have around 20 minutes time for discussion and to get back to the questions and all the speakers together. Okay, so I think we are ready to start. And Coralia, you are the first one, so please share your screen.
Thank you, Birgit. Yes, 1 minute. Okay, can you see it? Okay. Well, thank you, everybody, for being here. Good afternoon and good morning for the ones that they are in the other continent. Thank you for the effort to being here. I will present today our experience in aligning the data from the raw sniffer to the with the AMS. What is the experience here in the Netherlands and how we are doing it, and what are the important steps that we need to consider when aligning the data. This work has been mainly done by Anouk van Breukelen. However, she couldn't be here today. I will be, this was part of her PhD, and I will be just introducing you to the topic. First, here in the Netherlands, we have this sniffer that is was developed by Caltech, and we have 2 versions of it. It's a not dispersive infrared sensor, abbreviation NADIR, and it pumps like 1 liter of gas per minute. Inside the sniffer is heated to avoid condensation. It also has the particularity that it samples every 5 seconds. Well, there are other sniffers that they sample at different time, or you can adjust even the sampling window or sampling period. But this one, it comes by default by sampling every 5 seconds. It records methane and CO2 as well. It has the threshold that is for methane up to 2000 ppm, which we know that it might be low sometimes, but this is what we had. And for CO2, the threshold is 10,000 ppm. The data processing that we have, it's divided in three main parts. The first part is downloading the data and automatically filtering the data. The second part is matching or aligning the methane raw data from the sniffers to the AMS data, which it has the cow ID. And finally, well, it comes to the trait definition and to which is the phenotype that we are using. A little bit about how the data looks like. Here we have like a window of about 3 days. And if we can see, it goes from 0 to mostly 2000. You can see also there is a cut here. That's why I'm saying that probably it could measure a little bit more if we will have it. And but you can also see that there is a lot of data, and then there are some periods where we don't have data. They are empty periods. The data, if we zoom in into what it should look like, this is, for example, a visit about 4 to 6 minutes, and then we should be able to see some peaks. And then, for example, here you see about 500 ppm, and it goes down, and then it goes up. And in this case, we can count, well, 4 full peaks. We have sometimes some periods that we have, for some reason, it's possible that we don't have the data every 5 seconds. You can see the time here, and but you still can see the peaks. If we will measure every second, it will be more continuously this line, right? But and in this data visualization, we also can see some periods that they, or for some reason there is no data, or or you cannot see peaks, and then the records of the measuring is close to 0. And this, for example, is methane, and this is CO2, even that is for the same time. For some reason, the methane reader was not detecting any peaks or any changes in this period, when the CO2, it was able to detect some records. Then it's possible that we do have some CO2 records when we don't have methane records. And also we can see that there are some, in cases that the data is a bit erratic, then it's like we will consider that there is issue on the data, or with the reader, with the sampling. And you can also see that the sniffer can drift. In that case, well, in this case, you can go to minus 200 or even further. But this is how the data can look like. Enter into what our pipeline does. Those are a series of pipelines that they are written in Python. And what it does is just to first downloading the data from the Azure, this is this platform where the data is, and it allocated in CSV files. This is done by the first Python script. Then we have some filtering, and for that we subset per farm, per date, and hour, and we will keep only the subsets that they where the interquartile range is larger than 200 ppms. Because if not, this interquartile range is what is basically is obtained between the quartile 3 minus the quartile 1. And if this is smaller than 200 ppm, that means that it was not actually reading really well during this visit. And then we discard it. Also, if the mean is lower than 30 ppm, of course, we can see, as we say before, that it measured until 2000, then we also discard it. If we have the less than the 30% of the data should be within 10 ppm from the first two modes, like the most repeated records. At least, yeah, or less than 50%. And also, if it's above 2,500 ppm, that it shouldn't be possible because it's out of the range of the sensor, but we still have those data, then we also filter it or we exclude it. Then after we discard all outliers, that is, we will keep everything that is between the 0.001 quantile and this 0.999. The second part is the when we download the data from Azure and then we have it in the CSV files, this should be aligned with the AMS data or the Milken robot data that has the IDs. And this is going to be done. First, we synchronize both devices to internet time. That is basically dividing a day in 1,000 bits, and in each bit it has approximately 1 minute 26.4 seconds. And then once that both of the clocks of the sniffer and the AMS they are synchronized to this internet time, then we can match it, and based on this timestamp. And we also do some automatic plotting and randomized visual checks on of this how if this alignment is correct, to see if this alignment is correct. For example, here we can see in kind of pink color or the salmon color, then you see when the animal is in the AMS, and in the gray part is only when the animal is not present in the AMS. And on the y-axis, we have the methane on ppm, and the x is the time. Then it's expected that if there is no animal in the AMS at that moment, the methane record should be close to zero without those peaks. And then we can see it in the first example. In the second example, there is basically this space in between animals is really little. Then you don't see so much these zero records. But in the third one, we could see that still there is no animal in the at that moment in the AMS. We still had some measures of methane that could be caused that it was not well aligned, or it was most likely is that. And in the second part, you see it how it should be, that is methane close to zero, as no animal is present. Just about the trade definition, here in the Netherlands, CRV is the breeding company, and they are estimating the breeding values for methane, and they use average concentrations of the methane on ppm, and those are weekly average. And we prepare this data for them. What we do first is subtract what we consider that is the background concentration. That this is for that we use the 0.001 lowest quantile per farm per day. I know there is different approaches and different groups, but this is the one that we have been using, and we will hear later on what other groups are using. Also, we discard the first 60 seconds of the milking, and this is to account for the lag time, like the time that it takes to the methane to travel from the sampling to the reader. And this is just based on previous studies that's the most of the time that what it can take for this methane to arrive. It could be less, of course, but this is a standard for all the farms. That's what we use. And also we discard after 300 seconds of milking. And this is because after that, well, we know that the cow is at the bin in the AMS because it has some pellets to eat. But in the moment that after the cow eats the pellets, then the head of the cow can start to move. And then after 300 seconds, we see that there is more erratic behavior on the head of the cow, and then the start to be a bit erratic, the variation on the methane records. That's why we have discarded. Also, we discard records that after the filtering, the entire visit is less than 150 seconds because we consider that is not enough time. to calculate this methane average. Then basically the methane average will be calculated between 60 and 300 seconds. Then we compute the weekly means. For that, we do a diurnal correction on the visit means before to compute the weekly means. And this is due to the variation that it can be by hour of the day on methane. And then this has several explanations as the time of feeding, and we account for that. However, we have seen that when we average it weekly and our phenotype is weekly methane, that doesn't have a big impact to do this diurnal correction. However, it's really important if we are going to work with daily means. For this, we also have tried several approaches using 3, 4, 5 visits, up to 7 visits per animal required to calculate this weekly phenotype. At least now we are using at least 5 visits per week. This is a bit about the overview of the process, how, as I mentioned, it connects the sniffer to the database. There is a visual checkup when we have all the sniffers running to see if everything is working correctly. And then we have these Azure websites. Then we also allocate the new data in different CSV per farm per day with those records together for methane and for CO2. And also we start this goes to this Python script to download the data to the local computer, filter out bad data and match or align with the cow ID. And it goes also, this information of the AMS is provided by CRV. That is the also other information about cow ID, the date and time of the milking, and also additional other information that we will need later on, that is parity, breed, calving date. And then finally, this Python script to prepare the data for the genetic evaluation by adding this cow information that I just mentioned. In our work on the livestock project, we also investigate other phenotypes, that is not only the concentration or the average methane concentration per visit. We also explore the number of pigs per visit or per minute. And we have another phenotype that we developed together with the countries that participate in livestock, that it was the sum of the average of the two maximum values within each peak, the ratio between methane and carbon dioxide. Those new phenotypes, they have been incorporated to our pipeline, and now we produce also those phenotypes. Additionally, and this is not part of the pipeline, but we also have explored other methane phenotypes, like methane production based on formulas. And this is just an overview how genetically correlated are all those new phenotypes or different phenotypes, methane phenotypes, with our what I would call or the gold standard for the methane, sniffer methane, that is this average of the visit in ppm. And we see that the correlation is mainly high, except for number of peaks, but we also don't want to select for number of peaks. Then we have also like a low correlation with the tier 2 formula, but it's based on APCC equation, and it's based on a predicted dry matter intake that is suspected that this correlation is close to 0. Some work in progress. This pipeline or pipeline is continuously being updated by new ideas or some extra filtering that we consider as important to incorporate. And some of the new things that we are checking or we are working on is to check how well is the full coverage on the visit, because as I mentioned, or I presented in the first slide, sometimes the sniffer was not measuring every 5 seconds. We have a bit of gaps, and we want to check how is this, if it's really a problem, or when we should, after, if we have a gap for like 2-3 points, like 10-15 seconds, if we should discard that part or if we should keep that visit. We are investigating on that because we have seen it in our data. Also, we are working on maybe to define a minimum number of peaks per visit. We have seen, for example, in some cases that there is like one giant peak that is just like one peak, and then it goes to a plateau, and then it goes down. Then we can have an average concentration per visit, but probably it was something going on with the sniffer or with the reader that is not actually reading this variation or like the different peaks as we would be expecting. Then that's why we consider that maybe we should have this minimum number of peaks per visit. Additionally, we are also working a bit about with repeatability of the data. We are calculating the repeatability per farm per date per visit, per farm per date. And then we can see that in some cases we have a really low repeatable data, and then we are also planning on put some thresholds on the repeatability of the data. That can be 0.1 or 0.3, depending how strict we want to be. And this also has an impact in our genetic parameters estimation. Well, that's it from my side. And well, if you have any question, well, as Birgit said, you can put it in the chat. Otherwise, if it's not possible to answer it here in this webinar, you can also contact us by email. Thank you so much.
Thank you very much, Coralia. So as said, questions please in the chat, or we have time then after all the presentations. So we would move on now with the next presentation, who is from Oscar Gonzalez Recio from the University of Edinburgh. Oscar, can you share your screen?
Yes, thank you, Birgit. Can you see in full screen or the presenter's mode?
Yes, it's perfect.
Okay. Okay. Thank you all for being here. I will try to explain in this little amount of time that we have what we do in our case. The process is similar to what Coralia has explained. We just use different softwares, and I will tell about the particularities that we had in this case, in the case of Spain. I will go briefly through the sniffer setup, how they are installed in the sniffers, then data processing, and what is the output of the program. So the current setup is that okay, we only until now we're only working with farms with milking robots, and we set up the sniffer depending on the farm. We can set it here very close to the milking robot, or then sometimes we need to put it out depending on the space that they had for the sniffer. We had it installed in different places. The sniffer is connected through this tube to the feed bin, and it measures every second until every second, and it will register all emissions from the cow when the head is quite close to the feed bin. We do manual data download from AMS, so we need to go to the farm and download the cow traffic from the milking robot. Since we moved the sniffers from farm to farm, once we get the sniffer, we can download the data from the sniffer every time it's moved. And then at the same time or later on, during the following days, we can download the data from the AMS. Importantly, once we install the sniffer, we need to synchronize times in the sniffer and in the milking robot so that they are setting at the same time, same second, and same. Sometimes we have problems with the time saving because one of the devices changed to the right to the actual time, but the other didn't. So sometimes we had some problems for that. So it's important that both devices are synchronized and the timestamp are the same in the data. It's also important the lag time in the sniffer. So the lag time, we define the lag time as the time that the gas takes to travel from the feed bin to the sniffer sensor. So it may be some delay since the cow exhale methane until the sensor detects it. So we measure it at the beginning and at the end of the trial. We release some known gas at a known concentration in the feed bin, and we count how many seconds it takes for the sniffer to register that gas ppm. That's our lag time, and we registered at the beginning and at the end of the trial. In this time, we can discount this time from the sensor and match correctly the time that the animal was providing that gas information to the sniffer, because there may be some delay between the time in the AMS and the time in the sniffer. So we synchronize the clocks and we take into account this lag time to synchronize the data. So these are the raw data. This is what we get out from the sniffer. This is date and time, and then information about methane concentration and CO2 concentration. We can have other information like temperature, pressure, and more information depending on how much or how many cards the sniffer has built in and can provide to the data logger. This is the file from the sniffer, from the AMS, from the milking robot. And of course, it depends what software you have in your milking robot. Sometimes the software that they have in the different farms is different, so we need to homogenize this to have this kind of formats in which we have the ID of the farm of the cow. Basically, is the collar that they use. This is the ID for the robot, and we have here also the timestamp, time in the robot, milk production, how much time it gets. So this is milking time and time in the robot, and then some ID, additional ID of the cow. And we're going to combine these two files, and the output from this, from what I will explain later, is a file similar to this. I cannot minimize this. I don't know why. Okay. Well, it is the cow ID, the date that the cow entered in the milking robot, the production, time in seconds, and then all traits for methane during that visit. So at the end of the processing of the files, we have information from each visit of the cow. That will be the output of the Java program that we use. To process these files, we use a programmed pipeline written in Java. It's an executable file with 3 input parameters. It's executed like this in any terminal. It can be it works in both, well, in Linux, in Windows, Mac, and also all the 3 main operating systems. You need to call the program, and then your input parameters are the traffic file, the sniffer file, and the lag time that between the sniffer and the AMS. What it does, and I'm showing here just pieces of the code, is first read the files, the AMS and the sniffer files, with the cow transit and the gas concentrations from sniffers. Then it reads through the files and finds and compare the timestamps in both files, taking into account the lag between the sniffer and the AMS. And when it's equal, then assigns the sniffer data during that milking to the cow ID from the milking robot. We consider the whole visit, the duration of the whole visit, but we only account for the measurements during the first 5 minutes. Once we have identified what measurements from the sniffer belong to that cow at a given time in the AMS, what we call visit, then we compute the baselines for methane and CO2 as the average of the 5 lowest observations during that visit. This is our baseline, so we are computing an independent and specific baseline for each milking and each cow. Then we compute the average for the methane and CO2 observations after subtracting the baselines. That will be one of our main traits, mean methane and mean CO2 concentrations. We compute also the ratio between these two averages, methane and the CO2. And then we also detect the eructation peaks. To do this, we have like a specific piece of code in which we calculate the slope in running windows of 5 observations. And then when we determine that the peak begins, the eructation peaks begins, when the slope is lower than 5. Sorry, when the slope is higher than 5. Then the maximum of the peak ends when the slope is lower than -3. So it means that the observations are decreasing, and we determine that the peak ends when the slope is again larger than -1, so it's more or less flat. That's how we determined when a peak is in our data. Of course, these parameters are subject to fine-tuning depending on the sniffer specificities. Some sniffers measure higher concentrations. Some of them measure during every second, others every 5 seconds. So these are subject to fine-tuning depending on the specificities of the setting and mainly to the specificities of the sniffers. So far, our program does not estimate this or have not any way to fine-tune these parameters. So they are basically manual fine-tuning. And then once we have all this information for each visit, we calculate the number of peaks during milking. We also calculate the area under the curve, and we calculate the maximum values within each peak, which is the average of the two maximum values, as Coralia said before. And those traits that are not average per second, we provide the trait is expressed in units per minute. So number of peaks per minute, area under the curve per minute, or the maximum values of peaks per minute, so that they are homogenized, standardized to a given time, and they are not dependent on the length of the visit to the sniffer, to the milking robot. So this is basically the phenotype definition that the output of the program provides. It's the mean methane concentration by second, sum of peaks also by second, sum of peaks, the sum of the maximum peaks of methane emissions, the area under the curve, and also the ratio of the means between the ratio of the methane mean and CO2 mean. And we also provide this, not here, but we also provide the mean CO2 also by second. So we have all this information by visit, and then we compute the weekly average in a post-processed way using an in-house R script. So the output that will be this one, this is the output per visit. We compute the weekly averages for each cow. And each cow may have between 3 and 5 visits per day. So we filter these visits. I will provide information about our filtering. Once the data are filtered, the visit data are filtered, then we average them per week. And in a post-processing process, we also compute two different traits, two different conversions from methane concentration to methane production in grams per day. We use a Madsen equation, and we use also an in-house equation that is under review. I may provide some information if we have time briefly. We can say that there are large genetic correlations between phenotypes. Also, as Coralia mentioned, we have large genetic correlations in our data. This is like a graph of the different phenotypes definitions that we have. First, this will be like the average of all the methane measurement during the visit. We detect the peaks here. So we detect 1 peak, 2 peaks, 3 peaks, and then we average them by the minute. We compute the maximum values per peak, which will be the average of these two values. Usually these two maximum values are very similar. And we average them again by minute. The area under the curve is all the shaded light blue area here. So we sum all these values here, and again we standardize that per minute. And the maximum number of records of the measurements that we consider during the visit is a maximum of 5 minutes here. Then, as I said, we try to convert ppm to grams per day. I'm not going to, because it will take us some time. I'm not going to into much detail on this. But what we do is for each comparison group, we calculate the expected CO2 emissions per cow using some commonly used equations like the one in Pedersen et al. 2008. And we estimate what is the CO2 production from the sniffer sample. This is a sample. This is not the real CO2 emissions. So we have two different distributions, one for the sampling amount of CO2 that we have in the sniffer, and the expected one from the equations, from the CO2 production equations in the literature. So what we do is to standardize these two distributions so that they overlap. And then once we have this, we just use this conversion formula that is also used in other in most of the other equations to convert from ppm to grams per day or liters per day, in which we use the ratio between methane and CO2, and we use the production of CO2 in liters per day that we obtain from this expected distribution based on the expected distribution and our observed production in the sniffer. Then we use the density of methane to convert to grams per day. Again, this is the one of the output files, for instance, from one farm. We filter out these records. Some of the filters that we use is we discard measurements where the CO2 concentration is lower than 2500. We also use this filter to discard measurements above or below 3 standard deviation in the comparison group. We also remove cows that have less than 5 records per week or more than 35 records per week. We remove weeks with less than 5 records and animals that have only 1 week of records, because we have the sniffer like several weeks. So if one animal doesn't have enough records for that week, then we remove the whole week. Specifically for CO2 records, we do the same. I think that I already mentioned this above. And for the ratio, we discard measurements with a ratio that is above 0.3, and also that are above or below 3 standard deviations in the comparison group. We average data per week for consistency. They provide more reliable heritability estimates. We have checked this in our data, and when we use the weekly average, the heritability estimates are more reliable. So with the output of this of our program and with the test day from the farm, we provide a report to each farm. We have internal reports. For instance, what is the number of visits per cow in the farm? So cows that are out of the expected distribution, they are discarded. We also check for the distribution of the methane phenotypes. Usually they have this long right tail distribution. And we also have each of these will be a cow, and these are the box plot for the measurement of the different visits. So we can also detect if one cow is out of the expected distribution, and we filter it out. In terms of the reports of the farm, we provide this kind of reports. Here we provide information for all the cows. So each dot here is a cow. And on the x-axis, you can find the milk production, and on the y-axis, methane emissions in grams per day. So we take a look at those cows that are not producing enough milk production, but they have large methane emissions. Sometimes it's because they are at the beginning of the lactation, and that's okay. Some other times we identify cows that are in the high emitting group. We provide also an HTML file with more information that I will show after I finish this presentation very briefly. And we also show some comparison of the farm with other farms. And then, for instance, I just covered the name of the farm here, but this is a farm that is emitting more methane than the average, but it's also producing more milk than the average. So we will be worried about those cows that are below the average for milk production, but still they are high emitters. So we concentrate on those farms and look at more in depth what's going on in that farm, and we provide some suggestions to reduce emissions in that farm. With this, I would like to thank you all, and thanks the people of the team, mainly from Naker, who are the ones that have like the very hard work on measuring the methane with the sniffers in the farm. And I will stop sharing this, and I will briefly show the reports that we provide, just internal and also external for the to the farms. Let me share another screen. This one. So this is the internal report. It's an HTML file from an internal R script. We said how many records we have, how many cows, the number of data or visits per cow, the distribution of different methane traits. Yeah, these are methane traits. Time of measuring for the sniffer during each milking. So basically, what is the distribution of the duration of the visit in the AMS? The same for CO2, number of pigs per milking, and summary statistics, histogram for the number of pigs, for the distribution of number of pigs, and things like that. And here we can identify if there is some cow that is out of the distribution and some correlations between traits within that farm. The report that we provide to the farm is similar to what I saw. Is each dot is a cow. We contrast here the milk production and methane emissions. We compare this the farm with other farms that we have data from, and we also provide some economic estimation of how much they are wasting in methane. If they are producing more methane than the average, then how much money in feed they are wasting, because these cows are producing more methane than what they should do.
Sorry,
I
I need to interrupt you. Sorry, because we are running out of time.
Sorry.
For presenters. Thanks a lot for this very nice overview also of the report that you provide to the farmers. If there is time,
sorry for taking the time.
The discussion, we are happy to continue here on this topic. So we continue with our next speaker, who is Lucas Alcantara from University of Guelph in Canada. So the floor is yours, Lucas. So please share your screen.
Right. All right. Good morning, everyone. Just give me 1 second. Okay. Good morning again. I just want to thank for the opportunity for being here this morning to present some of the work we're doing for the data integration for sniffers. Just want to highlight as well that I'm wearing 2 hats on this project. One as a consultant to develop this, and also as the data manager at the university to support the work with the students as well. So the previous 2 presentations focused on after you get the data, and I believe some of the other presenters will do the same. But today I want to focus on the upstream process and basically answer the question of how do we automatically and reliably get raw methane data from sniffers on dozens of remote farms to a standard central database. So the challenge that we approached was that we started with LactaNet in Canada, that they wanted to deploy sniffers across the country. And they started in Alberta and Quebec, and then expanded to Ontario and British Columbia. And a few months later, Qualitas also approached us to deploy this a similar project over there, where they would install sniffers across Switzerland. And later on, they started a different project that also expanded this pipeline to Austria and Germany. One goal for this pipeline was that the deployment would be location agnostic, so it doesn't really matter where the sniffer is, if it's in the same room or across the country or across the world. It would be able to support multi-regions. The goal for this is that we would ensure the integrity of the data and process all the sniffers in a consistent way, regardless of where it was. I think somebody needs to be muted. Sorry, I'm getting a bit distracted with the noise. And also we needed to scale for an efficient pipeline. So we needed a repeatable architecture, because I'm going to show numbers now. There are so many sniffers and farms, and you cannot put them all on the pipeline at the same time. There's the negotiation with the farmers to get them to join the project. So sometimes you need to add them as you go throughout the year. So it needed to be seamless. So add this sniffer today, another one in a month from now, and 5 in 2 months from now. So that we needed to scale as it went. Right. So bottom line, we needed to standardize the workflow for adding new sniffers and collecting new sniffers as the project evolved. So just a bit of an overview. In Canada, this project started with Leptinet in Alberta. So 10 sniffers in 4 farms, so more than one sniffer per farm in some cases. And then in Quebec, 25 sniffers in 14 farms, 14 in Ontario, 6 farms, 10 in British Columbia, 2 farms, and 2 breeds hosting in jerseys. A total of almost 60 sniffers. This number is, if I'm not mistaken, expected to grow a little more as we onboard new farms. And there are several organizations related to this project. So there's about 5 universities as well collaborating with this. So there's some commercial and research farms in Canada. In Switzerland, they have a bigger number of sniffers already. So in the whole country, they have about 64 sniffers in 57 farms. And with the new project that they're starting with the Brown Swiss, they are rotating 8 sniffers across Switzerland, Austria, and Germany. Right now we have 7 farms in the pipeline, but as in a year and a half from now, when they expand to Germany, there will be more farms over there too. So 72 sniffers, and there are several partners with Qualitas from different organizations that are actively looking into this data. So we want to talk a little bit about the challenges that we had to overcome for this project. So there was a clear need. So the clients needed to deploy moo loggers, TechnoSense sniffers nationwide. And the goal was that they wanted to take those high frequency sensor streams into a centralized queryable asset for their geneticists and researchers in general. So, but there are several challenges. I recognize, for example, from Oscar, he presented that he had to go to the farm and rotate them manually all the time. So that's a huge challenge in its own. And in this case, where we were not rotating initially, the biggest challenge was to pull all of this data remotely. So as you know, the internet in my house is different from your house, so we cannot communicate to each other. And we also don't want to have the farms open to the outside world, and we don't want to have the server that's collecting this open to the outside world. So we had to come up with a strategy to overcome private networks. There is also a challenge of unstable connectivity, and that is one that we really cannot control. So some farms have very poor internet connectivity, so some rely on SIM data, others on Wi-Fi, and I believe we only have a few that has a hardwired internet connection. The other, one of the reasons that this is a challenge is also the reason why a power outage is a challenge, because in 2 cases, you lose. The first one, you don't get to pull the data, even though the data is being collected. The second one, you do lose the data, but then the sniffer, the pipeline, when it tries to pull again, it will have to come back and get that data. So also harsh environments, the nodes of the sniffer get plugged, so we have to make sure that the data is coming, that the flow is not low. So get alerts to make sure that things are running properly, and you take action before it's too late. So there is here's a quick end-to-end overview. So imagine there are two different farms. They each have 2 robots. That data comes through a secure VPN connection to our ETL pipeline. So that runs on a coordinating server that can communicate to the farms, but the farms cannot communicate to it directly, cannot initiate a connection for security. They cannot talk to each other. So that data is extracted and validated in terms of is any data missing? Is it within range? Is it the expected data type? Ingested to a database, a SQL database, and then that is used to feed off alerts and data checks for health of this data, and then send email notifications every day in the morning with a summary of what happened in the previous day and also throughout the day. And I'll speak a little bit more about it. That central database also feeds a role-based dashboard where different users have different visibility, where they can inspect data visually, they can check the data health reports, they can check the logs from the pipeline, they can track events that they maintain. So when they calibrated, when they swapped a part, when they did all the operations, so they can correlate that to possible events on the data. As I mentioned, there are several collaborators, so there is a module as well to export data to external servers, and everything is auditable. And as a management system, you can also manage user farms, projects, and alerts and define thresholds. One thing that this pipeline does not cover in itself is the processing of the data. So once the data arrives at a raw format in this database or as CSV files, then either Lactanet or Qualitas will take over and process the way they see fit. So they will calculate their baseline, align their data, and do their research. Just covering on how we overcame the connectivity issue. So we deployed a VPN integration. So every sniffer itself is a node on a private national network. There are several benefits with it, but I can highlight that there is no port forwarding required on farm routers. So you don't need to open up the farm to the world, which is a huge security vulnerability. Each sniffer has their own static IP address that the coordination server can talk to, which is independent from the farm. And that also allows secure SSH to the sniffers, and also API access for remote troubleshooting and data collection. That also allows us to monitor these sniffers in real time. So they are pinged in real time to see if they're available, if they're connected. If not, we get alerts to try to address what might be happening. And also there are API health checks integrated into the management layer. So throughout the day, there are checks to ensure that the data is being recorded before a whole day is lost, basically. So this was built for reliability. So the project, as I mentioned, it started in Alberta and Quebec in the very beginning. So Moologger was, we had access to the early versions of it. So at that time, we had a direct post-grade extraction from those early versions. Now they don't make that available anymore. They have a very good stable API to pull data from. But we do have a mix of Moologgers in the country, and they're both active. So there's two ingestion paths for this data. And there is also some fault tolerance applied. So there is an auto catch-up function that tracks what was last extracted. So Ringrina said when the internet might be down, so as soon as the internet comes back, it will catch up with what was missed and update the database automatically. There is we have the exactly once semantic, so there is a prevention of duplicate records during those reconnection bursts. So there's no issues in that end, and also batch processing because there's so many sniffers. If we were to process them in a continuous for loop way, that would take forever. So then we apply the batch processing where multiple sniffers are processed at the same time, so the pipeline can finish in a shorter timeline. So regarding the monitoring, the practical aspects of it, with so many sniffers and very different scenarios. It is very important that the researchers can keep track on what's happening as it's happening, not after a week or a month after you pull the data. So there are checks for recording activity that verifies if the sniffer is reachable, if the data is fresh, if it's the number of records is growing as expected, and then they get daily summaries and periodic status throughout the day to give that a review and the ability to respond rapidly. There's also an alert logic that checks for CO2, CH4, airflow, temperature, and humidity in their absolute value. So if they're off specific numbers, they get alerts, but also a percent change of what their rolling baseline is. So if the sniffer has been given 600 ppms on average, if it drops to 400 or if it goes to 800, then they get an alert say, hey, this is out of ordinary. So it's not specific to a number. So that helps for the individual farms. And then all of these areas, they're categorized based on the severity levels so that they can see, okay, this is a warning, this is critical, and then they can prioritize the response. There is, as I mentioned as well, there are several partners. So there's access and permissions on their dashboard to make sure that people can only see what they're supposed to see. And there's this is based on a project level scoping as well. So there are several projects, so users can only see what they're supposed to see. And this is very good for institutional governance when you have multiple partners that contribute to this specific set, so they don't go over everything. So overall, this pipeline that we put together tackle three things. So it helps with a robust upstream process to improve the downstream processing. So then you get faster detection that can reduce risk of losing data to because of the bad quality. Routine checks help with things that can be flagged as an event during that, and then helps for the analysis later. So this was calibrated. That's why there was a change in the peak. So when they process the data, they have unique event IDs that they can match up to and see the reason why the data fluctuated, so they don't lose time on that. And also they get immediate alerts, which could be the difference between losing 1 hour or 1 day of data. So overall, this proactive monitoring ensures that the data integrity of the pipeline and minimize impact on downstream analysis workflows. So I do have a few pictures here that we can show at the end if there's a curiosity of the platform itself. I think I'm right on the money for the 15 minutes. And this is about it. Thank you.
Thank you very much, Lucas, also for keeping the time. Yeah, if there is interest, I think, and if we have time, so we can go back to your, well, looking at the overview of your pipeline. So coming to the last speaker of the webinar, who is Victor from Aarhus University in Denmark. Please, Victor, share your screen.
Thank you, Birgit, and good afternoon, everyone. I'm thankful for opportunity to present our work we done here at Aarhus University, and my work will be about the GIDA, an adaptive framework for automated processing of sniffers data. Here, automated, it means that during data processing, no human involvement is does not required, and everything is going in one step. And adaptive, it means that during data processing, every decisions and filtering is not based, or as much as possible, is not based on a hard-coded constant, where the program tried or method implemented try to infer this constant from a data, so hence be adaptive to data.
Victor, you're muted. I think.
I'm sorry. First, I will outline the entire framework to just give a broad view of that one. Then, by presenting GITA interfaces, I will give a brief inspiration about the program itself from a practical perspective. So how it can be used in practice. Then, majority of my talk will be dedicated to the topic of this webinar as different processes, describing different processes stages of data. Then I will summarize my work and give some very brief results of genetic evaluation done by our team here. First of all, as already been said, the majority of data is collected within AMS automated milking station. So we are not the same as our presenters mentioned, but currently we are working with data or adjusting our framework to work with the data where ID coming not from AMS but from different sources. But I'm actually lucky that I'm presenting last one because I did not include the description of data or issues with the data, and this part was very well covered by our presenters, so I don't need to talk about that one. But my statement is all the issues was described by Coralie and Lucas and Oscar. They basically in most cases are the same as here in Denmark. So our work starts when we collect the data to our internal storage system. When we have a unit of work, the GEDA software, which takes a portion of raw data and in one step automatically produce related portion of gas emission data. And this software is dedicated to have different purpose. Specifically, what is do pre-processing in terms of initial quality control and resampling, do data alignment, reliability detection, background correction, and related filtering. Finally, phenotypes estimation and produce data quality statistics. But this I would call the unit of work is require high level automation, especially if we talk about the production system. And for that case, to allow full automation on production system, we have another product. It's called the GIDA server. Then finally, we have a higher level which integrates the GIDA server. It's a complete database integration, and that besides, it's also dedicated for production environments. Besides, the job is done by GIDA server. It allows the efficient storage of data. Besides, it allows the online monitoring of processes going on site and allows very convenient reporting and visualization tools for current status of data. But today I will talk strictly about the GIDA, the lowest level of software we developing, dedicated strictly for data processing. First of all, for that one, I will show about interfaces GIDA use. So for that unit of work where we have to receive portion of data and deliver portion of emission phenotypes, we need to let the program know where to take this data and how much data we should take, and we need to provide some parameters if we don't want to use default parameters in order to let the program know in which way to process the data. For that one, we need to supply configuration file. Then obviously we need to supply AMS data, the major source of animal IDs and the sniffer data. As an output, we have alignment data, we have phenotypes data, and we have login data. There is different options we can provide. We can have either aligned data, either phenotypes, or both of this kind of data. And the login information consists of a description of data processing stages, collect some statistics, and final estimation of data quality and stuff like that. Here I give some small example of how the GIDA actually could be used. So right now you can see the screenshot of example usually I deliver with GIDA software. Here we organize our data based on AMS data. So doesn't matter how big gas emission recordings could be 1 week, 1 month, or half a year. That should be organized based on the specific AMS tension and has a configuration file. Here you can see configuration file for a robot called 101. And here the major information the user should provide is AMS data file, where to find it, gas emission data file, which is associated with the specific robot here. We organize our data in for robot 101 in 2 data CSV files. Then we need to provide which kind of information we need to extract from a MS data file. Then the same approach, we need to provide which kind of data need to be extracted from gas emission data file. And finally, because AMS data file could be huge depending on producers, it could have information, not only required information for processing, but some, let's say, milking information, herd information, and stuff like that one. Besides, it could have information for different robots. So that's why we need to provide points specifically which robot we need to process. And finally, the ways could be launched very easily through bash, like you can see from bash scripting. So we need to provide call the program itself and need to provide configuration file, and we are up and running. Here are some details about MS data. So in this picture, you can see only columns which is required for the program. But as I already mentioned, the number of columns could be variable and different information, but we need to provide within MS called keyword only those columns we need. And here we obviously need animal ID. We need start time for milking, end time for milking, and the information about which robot information should extract. A similar approach for gas emission files. Here we need basically only 3 major information: date, time, and 2 columns of gas emission records. And the position of these columns could be variable depending on time file format. And here in this example, you can see day and time in separate columns, but it's flexible. If a user can have daytime in 1 column, it could be provided in 1 column and as well. If there is extra information like sniffer ID, farm ID is in farm, it could be also provided and will be used in the program in output file. And here, the output file, as I mentioned previously, log file consists of information about runtime messages and warnings, processing stage summaries, processing data statistics. Optional is aligning data file. This is a gas emission file with a correct association with the cow ID. And here you can see the description of columns in the output file. And finally, we have phenotypes file is because we have 2 kinds of phenotypes, and each kind of phenotype is provided by visit or by day. So we have 2 possible outputs. The only difference is that trait 1.1 and trait 2.1 is daily average phenotypes. We provide all the necessary information like cow ID, farm ID, robot ID, sniffer device ID, day, and gas emission phenotypes. For the visit-based phenotypes, in addition, we output the background correction terms. And the purpose of that background correction terms, because it might be useful to use it in a linear mixed model and genetic analysis. And in our group, it has been shown that it improves model by using this as a fixed effects. Okay, so as a very first step, we do pre-processing. Pre-processing, it's include time consecutiveness check in the data, sampling gap detection. What it means if, as it have been already shown by Coralia, data is normally has irregular sampling, and quite often we have time difference between two consecutive records, seconds, sometimes minutes and hours. And here we detect such gaps. If the gap is more than 2 minutes, we will split the data on two separate data sets. And the reason is because we cannot reliably predict what is going on within this 2 minutes gap. When we do minimum duration filtering, it means that the data samples which are less than 1 hour, we are not going to process that one because it will consist not enough statistical information to do reliable estimates. And finally, we do range consecutivity check. So it means that the time range in the sniffer gas emission data file should fall within the range of AMS data file. Okay, very first step for data processing is data transformation. We do. What does it mean? For example, if you can see the MS data table, so we need to transform this data table into time series, rescale it time series. It's either from it's a binary signal from 0 to 1 or from -1 to 1. Sample it with a 1 second interval. The same we should do with gas emission table, data table. So we resample it 1 second interval and transform it to time series signal and rescale it either from 0 to 1 or from -1 to 1. And the reason for that one is because for our data processing, we use statistical signal processing methodology, and here it's important to have a specified data model. And in our cases, the data model is related to the following assumptions and observation. For example, these two plots, the top plot is a binary signal of milking event, and the bottom subplot is a gas emission plot, and you can easily see the similarity. And our assumptions is that basically gas emission data is just a noisy milking event data, and hence you can see easily from these two plots which are sampled from real data. So we can, according to our data model, our MS signal, it's a milking event binary signal, embedded in non-Gaussian noise, and we can represent the gas emission signal with this data approach. Before I'm going to talk about the data alignment, or how we call it, synchronization, I need to give some notation about the timing skew. For example, what is the timing skew in our definition? If you can see the plot of milking event, so this is data from AMS, then the same data from based on gas emission signal, we have associated milking event. And if we merge these two data sets together and start to calculate difference between starting milking event from both signals, or as staying the same, difference between ending of this milking event from two signals, we'll have the time difference. And this time difference, we call it a timing skew. And in a real situation, how this timing skew picture looks like, I will represent only 4 very simple cases sampled, but the picture might be very much more complicated. First of all, what you need to focus is timing skew is just, it can represent a time series, and it's have 2 important properties to note. First of all is the timing drift, and here you can see in these 2 plots there is basically no time drift, this is just a noise. And the second property is just a resetting of timing skew. So here in the left plot you can see the shift from 40-second timing skew to around 15 seconds timing skew, and the right plot is just within the timing skew within 1 hour. But the real picture what we spotted with resetting goes from 1 hour like here to 2 minutes or 2 seconds, with a huge drops in resetting of timing skew. And this is data like here I showed 20-day records data. Another picture is more complicated but more interesting to see. Here you can see the clear picture of drift, time skew drift. Here it's but it could be positive or could be negative with the different values of timing drift and the regular resetting of timing skew. Right plot is more nicely looks, less noise and more complicated with more embedded noise in the left. And here we have regular resampling within 30 days. Of course, this data is pattern obtained from Danish data, but I'm quite sure that if we dig in, we can see the same might be see the same picture in Spain and Netherlands as well. So the goal is to synchronization is to account with complicated picture of time skew changes. And that's why we do the data alignment in the way we are doing here. So we split the gas emission signal to the smaller sub-signals. Like this one, you can see the plot where we have a gas emission and we just divide it by smaller parts, and each part will be aligned independently. And here the duration of this subsignal is from 1 to 24 hours. And the reason why we divide it and have this small signal is in the catch, because the time skew estimated will be constant within one subsignal, and the smaller duration of this subsignal, it's more accurately will be estimated timing skew, more accurate estimated the resetting of timing skew and estimated drift, accounted drift. And vice versa, if we increase the statistical power, but with the following consequences. Next, what we do time estimation. First of all, we take each subsignal and do cross correlation with Milkit event time series. So basically, we just shift this signal along with AMS data, and in order to estimate this parameter. So basically, according to our data model, our goal by calculating cross correlation along the MS data is to have unique pattern here in a gas emission signal, and our goal is to find the similar pattern, unique pattern in AMS data. When these two patterns will match, we'll have huge spike, and it's will be easily detected by this parameter. And then we find the difference between start of gas emission of this signal and milking event time series. Then we do estimate timing skew, but it's the height of the spike will depend on how much noise in the data, and this means that if we can spike is very distinctive, we can easily detect correctly timing skew. If the spike is quite low or even not visible, we can make statement that the data is really unreliable, and the reason could be is because it's too much noise or some fault happens on site with the sniffers. And but this signal length, subsignal length is can be managed through configuration file by this parameter, or even more, it could be optimized based on the best data quality processed by the program, if we put a minus, for example. But based on our optimization on our internal data, you can see this distribution. Most of the data, for most of the data, we have optimal signal length, subsignal length is 6 hours. And here, brief picture if how with random. I will describe later, but for this estimation, we use a linear mixed model on entire data to calculate repeatability values and genetic and residual random effect and residual variances. So left plot is showing the random effect variance, normalized one, for CO2 and methane data depending on signal subsignal length.
Victor,
And
I'm sorry, I need to interrupt you as well. Otherwise, can you come to an end, please? Because otherwise we do not have time for any questions.
yes, okay. Some results, it's, so yeah, we do filter and background estimation, of course, with this polynomial model. We also do outlier correction to pick up with peaks, and we do milking event visit-based filtering, as already mentioned in other pipelines. So we also do phenotypes, and our phenotypes based on simple average and average based corrected by sampling rate. Okay, so and the importance, because this the trade based on sampling rate is more stable to different sampling rates. So it's quite important observations to note to merge the data for and correct it for different sampling rates. So we also do estimation of data quality, and our results of based on linear model heritability estimated on our data. You can see this picture is around 0.13. So as in most cases in our, I believe in our data pipelines. So, and I will also do talk in ICAR 26 on 4th of June to talk about our server solution and database solution. So that's it from my side.
Thank you very much, Victor, for this overview of the HEDA software. We do have some questions already in the chat. Some have already been answered. Maybe we take one question for each of the speakers. We do have some minutes left. I think your questions are for Coralia. Those are answered in the chat. So there is a question for Lucas from Faisal. What is your advice on how to organize raw data storage when it comes to many number of sensors per farm?
Yes, so I already replied that to Fazel. So we basically do project sniffer year, month, and day file. So there's an example on the chat over there.
Thank you.
No problem.
Are there more questions? Take the chance. We do have some minutes left. Anyone just raise the hand? Faisal?
Yeah, I just ask a question from Victor if he can respond it. So my question is, when our sensors, because one of the sensors we are working with, it's sampling not based on, for example, every 5 seconds or 10 seconds. Is it statistically sensible to to force every visit before doing functional PCA? So, sometimes could be 10 seconds, 7 seconds, or 12 seconds.
I'm not sure I do correctly understand what the question is about. I understand it's about the problem with sampling and how to deal with it. But could you repeat the question a bit?
So what I mean is, if it's not so, because the sensors you're working with, it samples, for example, every 5 seconds. So then you're doing functional PCA, and you can see the curve. But what if the sensor is not sampling regularly, like could be every 7 seconds between two data, and for the next one is 12 seconds, next one,
Okay.
3 seconds.
Okay, I got the question. First of all, as I already mentioned briefly in my presentation, we need to do correction for sampling rate. But with irregularity in sampling, this is not something very unusual. We see this quite often. And by data processing, at least in GIDA, we do resampling of a data to regular sampling interval. So that is irregularity in sampling will not affect data alignment and phenotype estimation. At least during phenotype estimation stage, we do correction for sampling rate.
Thank you.
Mike?
Yes. Hello. So we're about to install 25 of these things across the UK. So I'm just wondering how do I get access to these pipelines that seem to be doing the job that we would have to do if we weren't part of this group?
Very good question. Who would like to start regarding availability of the different pipelines?
I can start. I can see you have a moologger there behind you.
Oh, so we do. So we do.
Yeah. So the pipeline we built in Canada and Switzerland is commercially available. So you can reach out to me. I'll put my email here.
Yeah.
Lucas at. And then we can chat more.
Okay. Good. What about the other one?
So in our case, sorry, Victor, would you like to go first?
No, please continue.
Continue, and then Victor.
Yeah, in our case, so far we've been working with collaboration agreements. We are investigating if we could build this program in an R package so that it will be freely available, but it's not yet, and I don't know if it will be. But I'm happy to have conversations with you, Mike, and see what will be the options in our case.
Okay. All righty. What about you, Victor?
More or less the same. If you are interested, just write email to us. I can say just right now, GIDA itself, which is doing major work, we're going to distribute free for research purpose. But if you might interested in production environments, GIDA server or GIDA database integration, so it should be on also on commercial basis. But again, if you're interested, just contact us. I will be happy to respond.
Smash, will do. And those answers were equally good as my question.
Yeah, I think it will be the same also for Wageningen. I mean, ours is not that fancy as a software yet. It's just like a combination of several scripts. But yeah, we could also help if it's possible.
Smash. All right. Well, thank you very much. All really interesting and highly appropriate. Thank you.
Thanks, Mike. Just to mention as well, so for some of this work is also within the GMG initiative, so the material will be available. So also the information, maybe not, well, it's currently under discussion, I think, regarding availability of the software for the GMG partners. But definitely, well, the basic information regarding what are the steps included in the different pipelines and so on will be freely available, definitely for the GMG partners. Okay, so I think we have reached the end of the webinar. I would like to thank all the speakers again for the really interesting presentations. And as Mike said, it's really timely. And we had I think 69 participants in the webinar, which actually shows really the importance and the interest in this topic and the need. All the material will be made available, so you will get the presentations, and we will also share it on the ICA Feed and Gas wiki page. And for this, I kindly ask the speakers if you could please send the presentations, what you would like to share publicly, just to gmg@wo.nl, and then we can distribute the information. Well, thanks a lot, everyone. Yeah, and have a nice afternoon. Thank you.
Thank you.
Bye. Thank you.
Thank you.
Thank you.
Bye.